Starship Flight 12 brought a lot of exciting successes, but it also revealed several issues and unanswered questions. What exactly caused the failure of Booster 19 after stage separation? Why did the flip maneuver look far more aggressive than expected? And with the new camera angles released after the flight, we can now see signs that the ship may have experienced issues just moments before touchdown. But honestly, the most important part of analyzing these failures is finding the solution, understanding what went wrong, and figuring out how to prevent it from happening again on future flights. And that, my friends, is exactly what we're going to explore today. There was also a lot of discussion about the booster failure after stage separation. A lot of people noticed that the booster seemed to flip far more aggressively than expected. During hot staging, Starship ignites its engines while it's still attached to the booster, and the thrust from those engines helps push the booster away. But on Flight 12, the booster appeared to get shoved sideways and downward instead of peeling away in a cleaner direction. That may have caused it to start tumbling or even corkscrewing through the air. You see, inside the booster are thousands of tons of super cold liquid methane and liquid oxygen. Normally, during ascent, all of that propellant stays settled at the bottom of the tanks because the rocket is constantly accelerating upward. But right after stage separation, everything suddenly changes at once. The ship lights its engines, the booster shuts down, the booster flips around, and then it immediately tries to restart engines for the boostback burn. That rapid sequence can make the propellant inside the tanks move around violently, almost like water sloshing inside a half-full bottle. Now, if the liquid propellant shifts away from the feed lines for even a moment, the engines could end up pulling in gas bubbles instead of a steady flow of liquid fuel. Rocket engines really do not like that. It's kind of like drinking through a straw when you get smooth liquid flow. Everything works fine, but once air bubbles get in, the flow starts sputtering and choking. A lot of people think something similar may have happened during the booster relight attempt. The theory here is that the flip happened in the wrong direction, or too aggressively. SpaceX had changed the flip system to make it faster, but something may have gone wrong with the timing or thrust control. One sea-level Raptor was supposed to help push the booster into the correct orientation, but instead the booster rotated strangely to the side. Some observers also pointed out that SpaceX probably already knew this could be a challenge to some degree. During Flight 12, they kept 5 booster engines running during hot staging, instead of only 3 like on earlier V2 flights. The thinking is that the new V3 ship creates a much stronger separation kick, so keeping more booster engines firing was likely meant to help hold the propellant at the bottom of the tanks and maintain stable fuel flow. The problem is that it still may not have been enough. During hot staging, Starship ignites its engines while still attached to the booster, and for a brief moment, the ship's exhaust plume blasts directly onto the top of the booster. Some people think that plume may have hit harder and earlier than expected, creating a violent shove that sent the propellant inside the tanks sloshing around even more. People have also been discussing the new V3 fuel system and whether it may have made the problem even worse. On the older V2 boosters, only the center engines and the middle ring of engines could restart after stage separation because they were connected to a smaller, dedicated fuel system called a header tank. The outer 20 engines were essentially cut off after the main engine shut down and couldn't participate in the boostback burn. But with V3, SpaceX completely redesigned that setup. The booster now uses a much larger central methane downcomer, basically a giant pipe running through the middle of the oxygen tank that feeds fuel down to all 33 engines. Because of that, every engine on the booster can potentially restart during boostback. That is a huge upgrade in capability. If all 33 engines can be used, the booster can perform the boostback burn much faster and more aggressively, which saves propellant overall. And saving fuel on boostback means Starship can carry more payload mass to orbit. The trade-off, though, is that this new design may also make the booster more sensitive to propellant sloshing during violent maneuvers like stage separation and the flip. Another possible factor was Starship's exhaust plume hitting one of the booster's grid fins during separation. Because the booster was already rotating oddly, the exhaust may have pushed it even harder in the wrong direction, making the roll worse. Now, an interesting idea people have brought up is that the booster may have actually been damaged right at liftoff, even though everything looked mostly normal at first. The theory is that the massive shock waves and vibrations generated during launch could have created tiny cracks or weak spots inside some of the Raptor engines. They may not immediately destroy an engine, but they could weaken components enough to cause problems later when the engines attempt to restart in flight. Part of this discussion comes from the exhaust plume pattern seen under the engines. People were comparing the shock diamonds, those bright diamond-shaped patterns visible in rocket exhaust. Some viewers thought Flight 12's exhaust looked blurrier or more uneven than Flight 11's, and they speculated that this might indicate unstable combustion or even material burning off the engines. However, others argued that this comparison may not really prove much. SpaceX changed the engine arrangement on Flight 12, with the engines positioned and angled differently than on previous flights. Naturally, that would also change the appearance of the exhaust plume, even if the engines were working perfectly fine. Still, the concern about launch shock waves is not completely unreasonable. When the rocket exhaust slams into the launch pad and the ground, it creates enormous pressure waves that can be incredibly violent. Historically, those kinds of vibrations have caused issues on rockets before, including damage to engine plumbing, shaking of engine bells, cavitation in propellant lines, or tiny structural cracks that only become a serious problem later during relight attempts. That said, it is important to remember that most of this is still speculation. Right now, there is no official evidence that shockwave damage caused the Flight 12 booster failure. At least, not unless SpaceX eventually confirms something along those lines themselves. So the big question now is, what can SpaceX actually do to prevent these kinds of issues on future flights? Well, if the booster really was being damaged right at liftoff by shockwaves and vibrations, then one possible solution is something SpaceX already does very well: the water deluge system. During launch, enormous amounts of water are blasted underneath the pad to absorb heat, dampen sound waves, and reduce the force of the acoustic shock waves created by the engines. But with Starship getting larger and more powerful, SpaceX may simply need an even more aggressive deluge system with much higher water flow to better protect the engine's plumbing and future payloads from those extreme launch conditions. Another possible improvement could involve anti-slosh systems inside the tanks or around the downcomer. These systems are designed to keep the propellant more stable during violent maneuvers, reducing the chances of fuel moving around too aggressively during staging and the booster flip. And honestly, this theory would actually be pretty good news for SpaceX. If the problem really was caused by sloshing or extreme flight conditions, then the engines themselves may not actually be mechanically flawed. Raptor engines are tested heavily on the ground, but the exact conditions created during this new V3 staging maneuver had never really been experienced before. In other words, the issue may not be that SpaceX built bad engines, but that the booster was suddenly thrown into an environment the engines were never originally designed to handle. Rocket engines work best when they receive a smooth, stable flow of liquid propellant. But once violent motion introduces gas bubbles into the feed lines, almost any liquid-fueled rocket engine can start losing thrust or shut down entirely. That's probably part of the reason why Flight 12 kept 5 booster engines running during hot staging. The extra thrust would help maintain acceleration and keep the propellant settled at the bottom of the tanks instead of floating around in microgravity-like conditions. So for Flight 13, SpaceX may decide to go even further. Some people think they could keep 7 or even 8 engines running during staging to stabilize the propellant more effectively and reduce the risk of sloshing during the booster relight sequence. Not long ago, SpaceX released new footage showing the upper stage of Starship landing in the Indian Ocean after Flight 12. These new camera angles gave people a much clearer look at how the ship handled re-entry, the landing burn, and the condition of the heat shield after the flight. Overall, the footage showed that the vehicle survived much better than many previous Starship upper stages, even though this mission was intentionally more stressful and included several tests. The landing sequence itself was very important. Starship came back through the atmosphere horizontally, then ignited its engines and flipped upright before touching down in the ocean. During this maneuver, the engines constantly moved or swiveled to keep the ship balanced. This is called thrust vector control. The engines point in slightly different directions to steer and stabilize the vehicle while slowing it down. One thing many people noticed was that the ship started rolling near the end of the landing. Some wondered if the vehicle was losing control, but honestly, this was likely related to the unusual engine setup used during the landing burn. On earlier flights, SpaceX used all three sea-level Raptor engines at the start of landing, then reduced to two engines near touchdown. On Flight 12, they only used two engines at first, and later switched down to just one engine. Using fewer engines gives the ship less stability and control, so when one engine shut down, the vehicle became more difficult to balance and started rolling more noticeably. The footage is important because SpaceX eventually wants to catch Starship in mid-air using the launch tower arms similar to how they plan to catch the booster. For that to happen, the ship will need to descend extremely steadily without rolling or drifting. It must stay perfectly aligned with the tower while almost hovering in place. So while Flight 12 was successful, the rolling motion at the end shows there is still more work to do before an actual catch attempt becomes possible. The upper stage also experienced an engine issue. One of the vacuum Raptors failed shortly after stage separation, and there was another visible flash during the event. Some people have been debating whether the RVAC failure might actually be connected to the booster problems. One theory is that debris from the booster engine failure may have struck the RVAC nozzle and damaged it during separation. If that's true, then the RVAC itself may not necessarily have a major design flaw. Whenever an engine fails during flight, the rocket's original trajectory instantly becomes invalid because the vehicle suddenly has less thrust than expected. At that point, the onboard flight computers have to quickly calculate an entirely new flight path using the remaining engines and available fuel. And honestly, Flight 12 seemed to handle that situation surprisingly well. Even after losing an engine, Starship still managed to stay under control and land very close to its planned target area, which shows that the guidance and engine-out capability are becoming incredibly robust. The downside is that the ship had to skip the planned Raptor relight demonstration on Ship 39. And that relight test was extremely important. Reliable engine relight in space is absolutely critical for Starship's future missions. Without it, Starship cannot safely perform true orbital flights because orbital missions require deorbit burns to return to Earth. Future plans like orbital refueling would also depend heavily on engines being able to restart reliably in space. That's why a lot of people considered the missed relight test one of the biggest disappointments of the entire flight, even though the mission still achieved major progress overall.